How semantic caching actually works, the technique that turns thousands of repeated AI questions into one answer you pay for once, and why it becomes a business requirement at scale. I've shipped LLM systems in production and worked on AI engineering at companies you'll recognize, including the caching layers that kept those systems affordable at scale. Most explanations of caching stop at speed. When most developers hear the word cache, they think one thing: speed. Make it faster. And caching does make things faster. But with AI systems, that's the smaller half of the story. The bigger half is money. Most developers think about speed. AI engineers think about cost. Look at it from the business side for a second. Every LLM call costs money. Every RAG query costs money. Every generated response costs money. And the same questions get asked over and over, all day long. None of that is the real problem on its own. The real problem is scale. Costs multiply as users grow. A small inefficiency that's invisible with 10 users turns into a large bill with 10,000. The waste doesn't add up. It compounds. So when you don't cache, you pay for the same work again and again. The same calls, the same tokens, the same retrievals, all repeated. Higher infrastructure costs, slower responses, worse scaling, and a pile of AI spending that brought you nothing new. So I'm going to show you what semantic caching actually is, how it works under the hood, and why at scale it stops being a nice optimization. By the end, you'll see why a stakeholder should care about it as much as any engineer does. Start with the basics, because the core idea is simple. A cache stores the result of your work you've already done. So the next time you need it, you reuse the result instead of paying to produce it again. The cache most developers reach for is exact match. You take the input, use it as a key, and store the output against it. Next time the exact same input comes in, you return the stored answer. For a lot of software, that works perfectly. But it breaks the moment you put a language model behind it, because people don't ask questions the same way twice. The same intent shows up in 100 different wordings. And to an exact match cache, every one of them looks brand new. Take a simple one. How do I reset my password? I forget my password. What do I do? Can you help me get back into my account? Same intent, 3 different strings. An exact match cache treats them as 3 unrelated questions, and you pay for all 3. Now, multiply that across thousands of users asking the same handful of things in their own words. You're paying full price over and over for answers you've already generated. The cache is technically running. It's just never hitting. Every cache miss is another bill. The problem is that an exact match cache matches text. It can't tell that 2 different sentences mean the same thing. To cache repeated intent instead of repeated wording, you need to cache that matches the meaning. That's exactly what semantic cache does. Instead of matching the exact words, it matches the meaning of the question. 2 queries that mean the same thing get the same cache answer, even when they don't share a single word. It works using the same trick as the rest of modern AI, embedding. You take the incoming question and turn it into a vector, a list of numbers that captures its meaning. Questions that mean similar things end up close together in that space. Closeness is the whole idea. 2 phrases of the same question land right next to each other. A different question lands far away. You measure that distance, usually with cosine similarity, and you get a score for how alike 2 questions really are. So when a new question comes in, you embed it. Then search your cache for the most similar question you've already answered. This is a vector similarity search, the same operation that powers retrieval in RAG system. Then you make one decision based on a threshold. If the closest match is similar enough above your cutoff, you treat it as the same question and return the cached answer with no model call at all. If nothing is close enough, it's a miss, and you fall through to the model. Put together, the whole thing is a small loop that sits in front of your model. Walk through a hit, a user types, "How do I change my password?" You embed it, search, and the closest cached question is reset my password at a similarity of 0.96, which is 96%. That's above your threshold. So you return the answer you already had. 0 model calls, a fraction of a cent. Now a miss. A user asks something you've never seen, and the closest match is only 0.4 similar. That's about 40%. Not close enough. Actually, it is 40%, by the way. So you call the model like normal, get the answer, and then store that question and its answer in the cache. The next person who asked it, in any wording, gets a hit. Be precise about it, because it confuses people. Semantic caching and RAG use the same machinery, embeddings, and vector search, but for opposite jobs. RAG retrieves context so the model can answer. A semantic cache retrieves an answer so the model never has to. That's why the savings are bigger than they look. In a RAG app, a cache hit doesn't just skip the generation. It skips the retrieval, the re-ranking, and the generation all at once. One cheap vector lookup replaces your entire pipeline for that request. The economics are lopsided on purpose. Embedding a question costs a tiny fraction of a cent. A full retrieval and generation costs a couple of cents or more. So a hit can be 100 times cheaper than a miss. And even a miss only adds a cost of 1 cheap embedding on top. And you get speed along the way. A cached answer comes back in milliseconds because no generation is happening. The thing developers wanted from caching in the first place, you still get it. It rides on top of the real prize, which is cost. The knob that matters most is the similarity threshold, and tuning it is the whole craft. Set it too high and almost nothing matches. So you keep playing. Set it too low and you start treating different questions as the same. The sweet spot is in the middle. That is where the savings live. Set the threshold too low and you start serving cache answers to questions that aren't actually the same. That's the real risk of semantic caching. A bad hit doesn't fail loudly. It returns confident wrong answer, and the user has no idea it came from a different question. This is the kind of thing that bites people. What's our refund policy in the US? What's our refund policy in EU? Those two questions can be 97% similar, and they have completely different answers. A naive semantic cache would happily serve the wrong answer, the wrong one to each one of them. The fix is to not let the unrelated things share a cache. You separate a namespace or use a namespace by whatever changes the answer. Per customer, per region, per language, per permission level. The cache only looks for matches inside the right bucket, so it can't cross wires. So you don't guess at the threshold. You tune it like an engineer. Start strict, where you only mirror identical questions match, so you stay safe. Then watch your hit rate and sample the hits for correctness. Loosen it slowly, only as far as the answers stay right, safe, and a little wasteful beats cheap and wrong. Quick aside, this is the kind of thinking I train developers on inside AI Engineer Launch, building AI systems that are cheap and reliable enough to run at real scale. I teach the full AI engineering path, and I've got recruiters working round the clock to put my people in front of the right roles and land that first AI job. The link's in the description if that's you. Back to it. So you don't cache everything. You cache the questions where the same intent should always get the same answer. Stable, factual, repeated questions. Policy lookups, documentation, definitions, common how-to questions. The boring high-volume stuff is exactly where the money is. And you don't cache the things that should change every time. Anything personalized to one user, anything time-sensitive like today's numbers, anything creative where a fresh answer is the whole point, cache those and you'll serve someone yesterday's data or somebody else's information. Now, the generally hard part, the one that separates people who've read about caching from people who've run it, invalidation. The moment the underlying answer changes, every cache copy of it is wrong, and the cache will keep happily serving the old one until you tell it not to. You handle it with a few tools. A time to live, so entries expire on their own. Versioning, so when the source data updates, the old cache is abandoned. And scheduled rebuilds, where you refresh the cache on a fixed cadence instead of hoping it stays current. The number you actually manage all of this by is the hit rate. What fraction of requests get served from cache? Your servings are simply that hit rate times the cost of the call you avoided. A 40% hit rate on an expensive pipeline is 40% off the part of your build that hurts most. And the hit rate isn't fixed. A cold cache hits nothing on day one. As real questions come in and get stored, the common intents fill up fast, the hit rate climbs, and your cost curves bend down as the cache learns what people actually ask. You don't have to wait for that though. If you already know the questions people ask most, you can warn the cache ahead of time, pre-compute the answers to your top questions and load them in. So the very first user gets a hit instead of a bill. And because a bad hit is silent, you watch a second number, the false hit rate. You sample cache responses and check that they were actually the right answer for the question asked. Your hit rate tells you how much you're saving. False hit rate tells you whether you can trust it. So a real semantic cache has a small dashboard behind it. 3 numbers tell you almost everything. How often you're hitting, how much you're saving, how often a hit was wrong. Manage those 3 and the cache stays both cheap and trustworthy. One distinction worth getting right, because the names collide, this is not the prompt caching your API provider offers. Provider prompt caching reuses the work of processing a repeated prompt prefix. Semantic caching skips the call entirely by reusing a whole answer for a similar question. Different layers, and you can run both at once. In practice, you often stack 2 layers. An exact match cache first, because it's instant and free when the wording is identical. Then the semantic cache behind it to catch everything phrased differently. Cheap check first, smart check second. And a cache can't grow without limit. So you decide what to drop. The usual rule is to evict whatever hasn't been used in a while, keeping the hot, popular answers and letting the rare one-off questions fall out. The cache stays small and it stays useful. Put it all in the request path and it's clean. The cache checks happens first before any expensive work. A hit returns immediately, a miss runs your normal pipeline and writes the result back on the way out. So the system gets cheaper the longer it runs. Let me make this concrete with something real. I worked on an internal AI tool used across an organization with thousands of employees. All day long, people asked the questions, and the pattern was exactly what I've been describing. Hundreds of people asking the same handful of questions, every one of them phrased a little differently. Same intent, endless wording. To an exact match cache, all of it looked new. To a semantic cache, most of it was the same question wearing different clothes. Without a semantic cache, that meant thousands of LLM calls and thousands of retrieval operations, millions of tokens spent generating answers we had already generated, sometimes minutes earlier, just worded differently. With a semantic cache in front of it, one good answer got reused across all the different ways people asked for it. The cost dropped sharply, and the responses came back faster because most of them never touched the model at all. The more users you have, the more expensive it becomes not to cache. A second example from the production side, we had a large data set that needed to be cached and kept current every day. So the cache rebuild ran on a schedule, not on a hope. The rebuild kicked off at 5 in the morning and it finished before 7, before the business day started. The cache was fresh and ready, and nobody using the systems ever saw the work it took to get there. That timing was deliberate. Rebuilding off-peak meant the heavy work never landed during business hours. It reduced load on the production systems, it kept responses fast when people were actually working, and it lowered the operational cost of the whole thing. That's the difference between a cache as a clever trick and a cache as infrastructure. Scheduled, monitored, rebuilt off-peak. Predictable cost, predictable performance, and a system that scales instead of buckling during the busy hours. A small-scale caching is an optimization. At large scale, it's a business requirement. Semantic caching pays off most exactly where AI gets deployed inside companies. Internal knowledge tools, customer support, documentation assistance, anything where a lot of people ask a limited set of questions. High volume, high repetition. That's the ground where caching prints money. All of this comes from a particular way of thinking, and it's the thing that separates an AI engineer from a developer who just calls the API. Before I send a single request, there's a set of questions running in my head. How much does this request actually cost? Not in the abstract, in tokens, in retrieval, in cents per call. If you don't know that number, you can't make a single decision about scale. How many times this same question gets asked once and caching is 10,000 times and not caching is negligent. The repetition is what decides whether the cache is worth building at all. Can I avoid another model call? Can I avoid another retrieval? Can I reuse work I've already paid for once? Those questions come before how do I answer this, not after. Reuse is the default, and a fresh call is the exception you justify. And how will this hold up at thousands of users? Something that's fine in a demo with one user can bankrupt you at scale. Thinking about the 10,000th user while you're building the first is the entire job. A developer asks, can we answer this? An AI engineer asks, how many times can we answer it without paying again? You can put a real number on it, on all of this. Your monthly savings are roughly your request volume times your hit rate times the cost of each call you avoid. Run that math and it gets dramatic fast. 1 million requests a month at 2 cents each is $20,000. Land a 50% hit rate and you've cut $10,000 off the bill every month for a layer that mostly runs itself. It's the same product either way, same model, same users, same answers. The only difference is whether you pay for each one answer once or pay for it every time someone asks it in a new way. At scale, that's the difference between a healthy margin and a finance meeting. The cheapest LLM call is the one you never make. This is the line between writing code that works and engineering AI that survives real usage. A developer makes the feature work. An AI engineer makes it work at scale, on a budget, without falling over the moment the traffic shows up. I noticed that none of this needed. No new model, no training run, no math you need a PhD for. Semantic caching is embeddings, a similarity threshold, and a good systems judgment about what to reuse and when. That's engineering, and it's learnable. If you've ever tuned a cache, watched the infrastructure build, or designed something to survive peak load, you already have the instincts this rewards. The AI piece is new. The discipline of making systems cheap and reliable at scale is exactly what you've been doing all along. The toolkit here is small and concrete. An embedding model, a vector store to hold the cached questions, a similarity threshold you tuned and watched, a rebuild or expiry strategy, and observability on your hit rate, your false hit rate, and your cost. That's a complete semantic cache. And it's exactly what companies are paying AI engineers for. Not just getting a model to answer, getting it to answer at the scale of a whole company without the build growing as fast as the usage. That scale is rare and it's valuable. Semantic caching is one lever and it stacks with the other. Route cheap work to cheap models, cache the stable answers, batch what can wait, Together, those are the difference between an AI feature that's quiet line item and one that's a crisis on the finance call. So the takeaways, semantic caching cuts your token spend because the cheapest call is the one you skip. And it cuts your infrastructure load because a hit never touches retrieval or generation. It improves the user experience because cache answers come back instantly. And it gets more valuable the more your usage grows, which means it pays off most at exactly the moment your costs would otherwise spiral. One honest caveat, because a CDR answer always has one. If your queries are almost all unique or every answer has to be personalized or live, a semantic cache won't help much, and a careless one will hurt. Caching is a bet on repetition. Make sure the repetition is actually there. If you take one habit from this, make it the cost question. Before you ship anything that calls a model, ask how much it costs, how often it will run, and whether you can reuse work you've already done. That single habit is most of what separates an AI engineer from everyone else. So this is what it comes down to. Most developers optimize for speed and stop there. The engineers, companies actually need optimize for cost and scale. And semantic caching is one of the clearest places that thinking shows up. If you want to think like that and build the systems that proves it, that's the whole reason I built AI Engineer Launch. I train developers in the real AI engineering stack, the things companies aren't hiring for. And I've got recruiters working round the clock to get my people in front of the right roles and land that first AI job.